Hello students, Mr. Carver here. Today is section 8.8. And we're going to be talking today about power series. Incidentally, today is Tuesday. So it's Aromatherapy Tuesday, so you should be sitting maybe on a leather jacket, popping popcorn, cooking bacon. If none of those apply to you, then get a candle out, please. Thank you. Now, we also talked when we did section 8.7 about polynomial estimations of functions. Now, there are polynomial estimations that when they are taken to be infinitely large will actually give you the functional value rather than just an estimation. For instance, we talked in class about the fact that e to the x could be written as 1 plus x squared over 2 factorial plus x cubed over 3 factorial, all the way out to the sum from n equals 0 to infinity of x to the n over n factorial. Now, if you take the limit as n goes to infinity and make this an infinitely powerful polynomial estimation, this polynomial estimation right here actually converges to the functional value, which is f of x e to the x for all x values, which is pretty fascinating. It's not even Friday, which means if you're looking for e to the 17th, you can take this polynomial estimation or this power series, plug in 17 for all the x's, add them together, and you will actually get the functional value to e to the x. In fact, if you were to graph this polynomial estimation, it would be the graph of e to the x. Now, there are other functions for which this is not true. For instance, if I take a look at arctangent of x, and incidentally, this can be written as the sum of x minus x cubed over 3 plus x to the 5th over 5, all the way out to negative 1 to the n. This is x to the 2n plus 1, all over 2n plus 1. And that's the sum from n equals 0 to infinity. This power series, polynomial estimation, will converge to the functional value, that is the f of x is equal to the arctan of x for x values that fall within the interval from negative 1 to 1 only. That means this power series polynomial estimation will only yield the functional value for the arctangent of x if you pick an x value that falls within this interval here. For instance, arctan of 0 or the arctan of 1/2, all that, when plugged into this infinite power series, will give you the arctangent functional value. Anything outside of that will result in a power series that diverges. So your goal for section 8.8 is to determine the interval of convergence. All right, so before we actually work on problems, let's take a look at how the power series, or how a power series is defined. So a power series will occur in a form that is similar to this. This is the sum from n equals 0 to infinity of a sub n times x minus c to the nth. Now, one of the things that gives away power series is that you will be dealing with infinite series in summation notation, which have an x in it, and they have an n that is listed in the sequence notation. Now, I should mention, we should add to your notes that C is the center of approximation. And if you recall, when we talked about polynomial estimations, we started off with the graph of y equals e to the x. And we built approximations around x equals 0. In fact, we used Taylor approximations around x equals 0. And we started off with a first-degree polynomial estimation that looked something like that. We then built a second-degree polynomial estimation, which looks something like that. And then lastly, we talked about a third-degree polynomial estimation, which looks something like that. Again, very good approximations around 0, a worse approximation at the farther you get from 0. And then we've also talked about the fact that you could move the center of approximation. For instance, if you wanted to have a Maclaurin polynomial estimation, you could move it anywhere off of 0 and build it accordingly. C is that number. So more precisely, in this section, you are looking for the domain. You are finding the domain of the power series. And the domain is the set of x for which, good morning, the power series will converge. So for a power series, centered at C, exactly one of the following will occur. Number one, the power series will converge only at x equals c. That is where it's centered. Two, the power series will converge over some interval. And we just talked about the interval of convergence for the arctan. That interval was -1 to 1 in that example. And then lastly, the power series will converge for all x values. And that was the first example we looked at. Y equals e to the x, that power series, that infinite power series, will converge regardless of the value of x that you choose. So the nice thing about power series is that you know they converge somewhere. It's just one of these three possibilities, either where it is centered, over a finite interval, or everywhere. And again, your job is to determine which values of x make the power series converge. And how will we do that? We will use the ratio test. All right, let's look at some problems. I think the first one here is fairly easy to see. You've got the infinite sum from n equals 0 to infinity. I've got 4 times x minus 2 to the n. And again, there are identifying features for power series. First of all, you've got x's in it and you've got n's. That is the giveaway for a power series. Also, I don't know if you see this, but this actually is a geometric series. They're not always this obvious, but let's just proceed as if we didn't see that. What we're going to do is we're going to take this sequence right here. We're going to use the ratio test on the series to determine if it converges or diverges. Let me rephrase that. We know that the power series converges. Our job is to determine the values of x for which it does converge. And so the ratio test will help us determine that. So if you recall the ratio test, I take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So I've got 4 times x minus 2 to the n plus 1 over 4 times x minus 2 to the n. And I'm going to set that less than 1 because I know for a fact that this thing converges. And if you recall from the ratio test, if the ratio of a sub n plus 1 over a sub n turns out to be less than 1 when you take the limit as n goes to infinity, I know that converges. So all I want to do now is clean this up a bit. So I've got 4's canceling. I've also got n of x minus 2's canceling, which just leaves me the absolute value of x minus 2 being less than 1. And now, it's nice. All I have to do is solve this inequality. So remembering back from Algebra 1, I've got x minus 2 is less than 1, and x minus 2 is greater than negative 1, which means x is less than 3, and x is greater than 1. So I know for a fact that the interval of convergence will go from 1 to 3. Now, the only issue now is checking endpoints, because when you solve this inequality here, you are just determining what I call the overall interval of convergence. You must check the endpoints. So the way I write the overall interval of convergence is, I've got question marks. I know for a fact it goes from 1 to 3. I just don't know what happens exactly at 1 and exactly at 3. So let's check those now. Let's do x is equal to 1. Now remember, these are x values. So when I plug this in, I've got the sum from n equals 0 to infinity of 4. And I plug 1 in there, that gives me negative 1 to the n. So what I have now is an alternating series. So I use my alternating series test. I take the limit as n goes to infinity of 4, and that is not equal to 0, so that diverges by the alternating series test. I then check 3. This is the sum from n equals 0 to infinity of 4 times 1 to the n, which is 3 take away 2. A sub n does not equal to 0, so this diverges by the nth term test, which means my final answer. I can go back and adjust this now. Take this and get rid of this. My overall interval of convergence goes from 1 to 3, not including the endpoints because of the tests that I just ran on that. So the answer to this question, the interval of convergence, will be from 1 to 3. Now, I did mention that this is a geometric series, if I take a look at that. So isn't it true that my r here has to be less than 1 in order for this to converge? And that is true only for these x values right here. All right, let's take a look at it. Just a couple more, and then I think we'll be good for the day. Let's do here the power series. I'm going from 0 to infinity of 3x to the n all over 2n factorial. So again, I've got x's and n's. This identifies as a power series, so I'm going to take the ratio test. We're going to take the limit now as n goes to infinity. I've got the absolute value of 3x to the n plus 1 all over 2 times n plus 1 factorial over the original 3x to the n, so I'm going to copy dot flop. That gives me 2n factorial all over 3x to the n. And I know again that that converges, so I'm going to set that less than 1. So this actually turns out to be 2n plus 2 factorial. So if I clean this up slightly, the 3x's cancel. That leaves me a 3x on top. I've got one more on the top than I do on the bottom. And then my factorials are going to cancel as well, giving me a 2n plus 2 times a 2n plus 1 on the bottom. So now I'm taking the limit as n goes to infinity of the absolute value of 3x all over 2n plus 2 times 2n plus 1. That's less than 0. Now remember what we're doing here. I'm taking the ratio test, so it is now n going to infinity. And you can think of x as being a constant. I realize that x can be any constant. Actually, what we're looking for is the value of x that is possible to make this inequality true. So as I drive n to infinity, regardless of the value of x that I choose, this ratio, or this limit here, will be driven to 0, again, regardless of the value of x that I choose, as long as once I choose it, I don't change it. So the limit on the left-hand side will be true for all values of x, because n continues to grow and will outcompete the top, driving the whole thing to 0, so regardless of the value of x, that inequality is true, which means my interval of convergence goes from negative infinity to infinity, and that is my final answer. All right, one more for you. Let's do the power series from n equals 0 to infinity of negative 1 to the n. I've got n factorial x minus 4 to the nth all over 3 to the n. And again, the mixture of x's and n's lets us know that we're dealing with a power series. So again, I'm going to take the limit as n goes to infinity using the ratio test. Now remember, this is absolute valued, so I can disregard this portion of my sequence here. This will be n plus 1 factorial. This is x minus 4 to the n plus 1. This is all over 3 to the n plus 1. If I copy dot flop the original, I get 3 to the n factorial, x minus 4 to the n. Again, this is less than 1 since it's a power series. I just need to clean this up. Now, I've got one more 3 in the denominator than I do in the top. I've got 3 in the bottom. I've got n plus 1 factorial and n factorial giving me an n plus 1 in the top. And similarly, the x minus 4's cancel, giving me an x minus 4 in the top. This now gives me the limit as n goes to infinity of the absolute value of n plus 1 times x minus 4 all over 3. That limit's got to be less than 1. Now, as opposed to the previous example, again, it doesn't matter, well, what I'm looking for, rather, is the value of x for which this inequality is true. And what you'll notice here is that regardless of the value of x, this portion right here is going to drive that numerator rather, to be larger and larger and larger because it's really n that's growing to infinity. So the only way in order for this ratio to be less than 1 is if x is equal to 4, making this portion 0. Actually, the number 0. And this is actually going to hugeness. So that is, in fact, determinate. So at x is equal to 4, it converges only at x equals 4. And for those of you who love interval notation, we can go 4, 2, and 4, including the endpoints. All right, guys. I'll have the homework posted on my website. Hang in there. Hopefully the video Support will help, and I will talk with you soon. Thanks.